skilled in verification and validation and test automation using LabVIEW. Orion Space is a company established in 2017 that focus on promoting space education among youths like us and creating a distinct field for the students to gain knowledge and explore the possibilities of space technology in Nepal. Mr. Prajapati and his team has made the first Pico-Satellite in Nepal called SANOSAT-1, SANOSAT-1, which is soon to be launched into the space. Guys, can you believe this? That is magical. The Pico satellite is equipped with solar cells and lithium-ion batteries to store the energy harvested from the sun. We will be getting more insight into this later on. And after being launched, this satellite, amazing satellite, will orbit about 500 kilometer altitude from the Earth's surface. One of the missions of the satellite is to measure space radiation, almost 7 kilometers, which is maybe the limitation or the maximum limitation of. I will ask Sir about more about this. Sir, look at this. He is making a history in the space history of Nepal. Orion has done so much to establish a name for Nepal in the space industry, and we are so glad that he is with us here. Rakesh Chandra, sir, it is an honor to have you here again. Now, I would like to give the floor to you. Please take on the floor. Thank you so much.
Thank you very much for the kind introduction. And well, I will share my screen just a sec. I hope everybody can see it, right?
Yes, sir.
Okay, perfect.
Yes, sir.
Okay, great. Thank you very much for your interest and time that you are here. So I will give a very basic introduction about space technology and space science. So I will not go too much detail, but during question answer, we can have more detailed discussion. And then I will also introduce like what we are doing in Nepal. So in future, when you are a graduate, like if you study engineering or physics, maybe you can one day work in Nepal in a space project. So without any further ado, let me just, okay. So I would like to start with our basic, the intuition we have, like we talk about sunrise, sunset, you know, but I mean, the view is giving you the wrong intuition, like sunrise and sunset is like something, sun is going around the earth, right? Because it rises in the east and sets in the west. So it seems like earth is there and the sun is going around. So this was the view of the solar system. We as a human civilization, you know, like how we develop our understanding about the solar system and the so basically this is still engraved in our daily conversation, like sunrise doesn't make sense and the sunset doesn't make sense because it's not the sun that goes around but the earth which is going around, right? So we have to understand like how we, from the early civilization till now, we have this solar system. And here are the like the basic development, like Copernicus was there. He bring this idea like, it's the sun that is in the center, not the earth. And Bray, he did some observation, but he could not formulate what is behind. But then Kepler came in, which you already might have heard the name, who bring together all the observations into the mathematical model, who said, okay, the orbit is, earth is going around the sun in an elliptical orbit. So he was there. So he gave 3 different laws. I will not go into detail now, like what are the laws, but then there came the Galileo. And then finally, what we have here, like Galileo did some observation with his telescope, and then Sir Isaac Newton. So this is the basic high school level physics, like we study about the gravitational force, right? So even before the Newton, there were other people who were able to claim that how the gravity is working, or how the orbital mechanics is working. Like basically there are many observations. So Isaac Newton was basically giving mathematical formulation what Kepler said. So basically Kepler would be the basic the idea general. Well, you can't say Kepler even, because Bray had these measurements and Copernicus had the idea. So this is not single man work. It's just a string of development, like how the concept evolves. So basically we go back here again. So we are still talking like sunrise and sunset. So the concept is giving you that sun is going around the earth, but then we now know that it's the earth that goes around. But still there took so many developments, like like 1473, by the time 1727, like let's say, or 1642, around this area, like 17th century. So it took quite a long time from 14th century to 17 to have this idea. And now we talk about the projectile motion. So if there is no gravity and if you shoot a cannon, it will go straight. And if you imagine like there's a gravity, the cannon will fall down. So this is the path which you have also studied in high school, right? Like a projectile motion. So projectile motion is any freely moving object in under the influence of gravity. So basically how the gravity defines the path. This is projectile. And maybe you already did some mathematics that the path is parabolic, right? So that's a basic idea. And this is the fundamental. Now you have to understand that this is how the satellite is going to revolve around the Earth. So you can imagine that the cannon which we shoot is very high in the mountain. And now we define like how fast the velocity is going to, shoot. So here it is. If the velocity is very less, I mean very low, it will fall on the ground. And then you'd say, okay, maybe I will have to shoot much higher speed, and then it will fall still little far, but still on the ground. And thus we can increase the velocity of this cannon until it goes around the Earth. So here it means that it's falling down, but still like the Earth is curved, so it will not hit the surface. Here the curvature of the Earth and the falling of the cannon, the projectile, intersect at this point. So we say that, okay, cannon is hitting at this surface. And then if you increase the speed, it goes further away and further away. And at one point, if we are able to increase the speed, it will, I mean, it is still falling, but the Earth, it's not, the surface of the Earth is like, the curvature of the Earth, and the falling, the curvature of the fall, they are like not intersecting. And thus, every time the cannon is falling, but then it is not able to reach the Earth's surface. That's why it's coming back again. So this is the basic, this is the basic idea, like how the satellite is going to work. It's simply that we have to shoot the satellite and it's coming back again and going round and round, just because it is not able to hit the surface of the Earth. And based on that, like we have different orbit, elliptical orbit and parabolic and hyperbolic. So basically these are also the speed dependent. The higher the speed, the more you're going further and further into the hyperbolic orbit or parabolic orbit. And once you are in this path, you are never going to come back to the Earth. Here you can see the circular path is coming back, and thus the satellite is going around the Earth. And here you have also elliptical path, but then you are still coming back and going around the Earth. But if you shoot very high speed, like then it will go away from the Earth, and the path, they do not come back. So you are like skipping the Earth. So this is also one possibility, that if you want to leave the Earth and go to the other planets or out of solar system, you have to shoot with a very high velocity, or you have to have accumulative velocity. I mean, basically we will see this during the question answer, like if you have some question like how to do that. because you have either one option, like in the very beginning you have very high velocity, or you are just pushing every time, and accumulative velocity you acquire, like so that you can skip the Earth's gravitational force. So this is just skipping the gravitational force of the Earth. So now you know that how to go away from the Earth, or how we can maintain the orbit of the Earth. Here you can see the Earth is going around the sun, and this white cube, this is the satellite, and satellite is going around the Earth. So you can understand that Earth has certain velocity which keeps the orbit within the sun. So Earth is going around the sun. Second phenomena, it's the again gravitational force, the pull, that keeps the object within the Earth gravitational field, and it's going around the Earth. So you can see that Earth is bound by the sun and the satellite is bound by the Earth. So, but still they are under the same principle. It's the gravitational force that keeps them bound and revolving around. So this is very simple. And now you have like, how do we put our satellite into orbit? Because we said that, I go back again. Here we said that if we shoot the satellite at the given or the necessary speed, it will go around and it will keep on revolving. But then how do we put our satellite at this point and then shoot? This is the biggest challenge, and that we can achieve by the use of rocket. So we have our satellite somewhere here at the nose of the in the nose of this satellite, rocket. So our satellite is somewhere inside, and the rocket will launch, and then it will go up into the like a required height. Basically, in our satellite, what we are building, it's around 500 kilometers. So from the Earth's surface till this point is roughly 500 kilometers. So I go back one more time just to remind you. The height we have here is 500 kilometers. But obviously, this is not the mountain hill that we have so high. This is just an illustration, right? So if we are able to go at 500 kilometer and then shoot our satellite or any spacecraft, and then able to maintain the orbital speed. I mean, you have to maintain the orbital speed, because if the speed is not enough, it will fall back. So this is very important. So basically we have our rocket that will take us to the very high altitude, which is in our case, it is 500 kilometer. And then the satellite will be launched from the rocket, and it will go around. So now the satellite will be in the orbit of the Earth. So this is the basic idea. But then we can also talk about, like, there are many different types of orbit. So basically here is some illustration, like how far the airplane can fly, roughly 10 kilometer high. And you have satellite, which we are talking, this is around here, like 500 kilometers. So these are some satellite images. You can see roughly around 500-600 kilometers. And above 1,000, there are also other satellites. And around this 3,600 kilometers, there are other satellites. And here is the moon, like 360,000 kilometers. So this is very far. So if we can compare the distance here, I mean, this is in a log scale, that's why they look very near. But then if you put them in linear scale, you can see that this is the orange band. This is the band where mostly our satellites are. This is where we are doing mostly the research. If you have heard about International Space Station, which is roughly around 400 kilometers, so this is the astronauts. They are revolving around the Earth around this height, like 400 kilometers. But then there are other satellites that you need to put at 36,000 kilometers, and these satellites are basically for telecommunication, because the time the Earth rotates about its axis and the time the satellite goes around the orbit, they are equal. And that means so this satellite is always above the given point, whereas the satellite here, they are going around, they don't stay above the head. Here at this orbit, the speed of the satellite at the speed and the speed of the Earth rotation, they match, and thus like every time the Earth moves, the satellite is also moving, and then they are always above the head. But whereas here the satellite is moving very fast. So like roughly, to give you the feeling, so if you are at this 400 500 kilometer far, it takes you 90 minutes to go around the Earth. So this is how fast the satellites are going. Like you are at this orbit, 400 500 kilometer, and the satellite has to go around the Earth, and it makes one revolution in 90 minutes. So that's very fast. Now talking about the satellites, like there are very big, small, nano, different size of satellite. And in Nepal, we are building these kind of satellite like Pico and Femto. I will show you like what is that, but still like the big satellites, large, medium, there are many classifications, but then they are like more than a ton or 500 kilometer, like basically 150 kilometer, sorry, kilogram satellite. These satellites are very common, and these like 1,000 ton or 500 kg, like these satellites are not so common, but these are by the big companies like NASA and government project. And small companies, maybe they are building like 10 kilogram or 50 kilogram satellite. And some universities, they are building 1 kilogram satellite. And now we come into play. We, as a private company in Nepal, startup, we are building like a Pico-Satellite now, like which is less than 1 kilo. So you can see here the picture, like this guy is holding a satellite, and he's also holding a satellite. So these are the types of satellite we are building now in Nepal. So these are like a pico, nano, or femto scale satellite, which are less than a kg or about 1 kilo. Why we are doing this? Like why building small? Because there are two things. I mean, we are the beginners, so we want to start from the basic and build very small. And also, like we don't have a huge budget. We don't have money to build a big satellite and launch them. So these are the thing, like how complex you want to make, because we are the beginners, so we want to make it simpler and smaller. And also the cost, because building big satellite is very costly, and to launch the bigger satellite is also very costlier. So uh, these are the factors that we have to select, like where you want to be. Because if you want to to build a bigger satellite, you have higher cost and more complexity. And if you are building this one, you can see the reference, like the hand is holding the satellite, and these are very small. And this is the one we are building now, and they are much cheaper and less complex. And then the other topic I forgot to mention earlier, but then I repeat. So the more heavier the satellite, the more you have to pay for the launch. It's just like you are buying a ticket for the rocket or the bus ride. So what we have here, the rocket will take you to the required orbit. In our case, roughly 500 kilometer. So this is like going from Kathmandu to Pokhara, which is, I guess, 200 kilometer something. I mean, we are not very far from the Earth's surface. Like, if I remember correct, Kathmandu to Pokhara would be roughly 200 kilometer. So, and Pokhara to Kathmandu, another 200. So from Kathmandu, Pokhara, Pokhara, Kathmandu would be some same distance as the rocket will take your satellite to this point. So it's not that far, 500 kilometers. But the point is, if your satellite is heavy, the rocket will need more energy to lift up and put it here. Thus, you have to pay more. Just like in the if you talk about like bus ride from Kathmandu to Pokhara, you have to pay the ticket, right? It's the same, like you have to pay the ticket for the rocket ride, and this is very expensive if your satellite is heavy. So this is also the reason why why we are doing very small satellite, because it's cheaper to launch. And then there are other pocket cubes. I mean, they are like Eagle 2, Liberty, Smoke 1, Fossa 2. I mean, these are the different satellites which are already launched, and they are, not all of them are in space now, but some, like Fossa 1, not 2. Fossa 1 is in the orbit. It is going around the Earth. Smoke 1 or similar is also in the orbit, which is going around the Earth, and this was already on the orbit, and it is already well. And there is also the lifetime, which I did not put on the slide, but basically so maybe I will go a little back just to give you the idea like what I was saying in here. So basically, when the satellite is going around, there are like different forces, external forces that try to resist. And that means you are decreasing the height slowly. Every time you are going around, you are dropping the height. After some time, let's say roughly when you are around 150 kilometer, the atmospheric density is very high, that the satellite will disintegrate. It will burn while revolving around the Earth, because there will be more higher friction between the atmosphere and the satellite, and they are moving at very high speed. So you have to remember that if you do not have any mechanism to keep the satellite in this orbit, it will slowly disintegrate and then slowly come into the height will decrease slowly, and at one point it will burn before it hit the surface. So this you have to understand, and for that you can have some mechanism to keep the satellite in the orbit for longer time. So if you do not have that, basically the satellite has a lifetime. That means it will come down slowly and burn. So the time between the orbit until it's burning, it burn, this is known as a lifetime. So now you understood that satellite that you put in the orbit eventually come down and then it will burn. So they have also the lifetime. And this satellite is already burned during the re-entry. So that you have to understand. Well, then why do we need to build the satellite, or what do you want to do with the satellite? This is very important. Basically, it could be some technology demonstration. You want to show new technology, like, wow, we can do like this. And maybe you want to see some science, because in orbit, the gravity behaves very, not really behaves different, but I would say like very, well, I would not like to call it zero gravity, like it's not zero. Some we call them like a microgravity. So the object or the biochemistry or the biological systems, they behave a little different in the Earth surface, and also while it's in the orbit. So we can do some biological science or material science kind of thing to test. An educational project, like you want to learn about the rocket, you want to learn about satellite, you want to learn about space science, then you can do an educational project. And some commercial, like you want some commercial application, like take a picture and you can sell the picture, take a picture from space. So there are many different objectives, like you can follow different. But then here, the educational project is our target. Like we are building this for learning, and we have lots of students involved to build this satellite. And before building satellite, we were building the, this is not the real satellite. It is called CanSat. This is the model to teach how the satellite works and what are the building blocks of satellite. So basically, if you look at the computer, you can see power supply, microprocessor, and the mouse, keyboard. Similarly, if you look at the satellite, you will have similar thing like antenna to transmit the signal and receive the signal. And you have these controller, power supply, the battery. So basically, we are learning about this basic building blocks of satellite. And also, we were building these ground station, like because once the satellite is orbiting around the Earth, and maybe you want to take a picture from this space, but then how do you get this picture? I mean, the satellite is always, going around and taking pictures, but if you don't have a communication that the satellite could send back the picture to you, then it doesn't make sense. So we will need a communication link, right? So satellite takes a picture and it will send the picture down to the Earth. And also you will need a ground station where the signal can be captured and then reproduce the picture. So for that, we need the ground station. Now talking about the Pico-Satellite, this is the same or similar satellite we are building. This is called Pocket Cube, and this is 50 or 5 centimeter cube, and it is cheaper to launch, and it's small. That's why it's cheaper, and it's also cheaper to build also, and also it is not very like, basically building satellite can take you 5 to 10 years, but building small satellites, it can be few months to a year. So 6 months, 1 year, or 2 year. So like, let's say 2 years project is a typical suitable time for the students to involve, understand, and build the satellite. Here is a specification of our satellite that we built in Nepal. You can see the picture and the CAD 3D model, how what is inside you can see here. And this is the picture of our satellite. And here is this some specification like 5 centimeter cube, less than 250 gram. And yeah, but so what is our mission? Our mission is sending small SMS kind of messages, like you can send small message, short message, and then you send it to satellite, and satellite will send to the other person who can listen to your message. So this is one application. And the other application is to measure the radiation in the space. So our satellite is going around the Earth in this space, and it will measure the radiation, and the measurement value is sent to our ground station. And you can see the sensor is this one, the very small dark brown. So this is the sensor that takes the measurement of the radiation, and via this antenna, you can see this antenna here in the picture, this one, and that antenna will send the signal to the Earth. So these are the name of the students and engineers who were involved in this project. So we are very happy that finally we are able to build the satellite, and we will be launching very soon. As per now, we have the date in April 2021. So we are very excited. Well, this I will not go into detail, but just to give you some idea, like we have electrical power supply system because we have a solar cell. So if I go back, this is solar cell, and here is also the solar cell. So the surface of the satellite is covered with the solar panel or solar cell, and then this will generate the energy, or it will charge the battery which is inside via the sunlight. So you have the sunlight, and then it will take this sunlight and convert into energy and charge the battery, and that battery will help to power our satellite. So basically this is the block diagram just to show you that we have a solar cell, and then the charger, and then the battery here, and then the power the protection circuit, and after this part is our satellite that you are going to power. And also we have controller, microcontroller, which you might have used, So similar controller we are using for like when to send the information, when to take the radiation measurement. So this is control. And the communication system, I already mentioned that whatever you take measurement and you need to send to the earth, we have this communication block, and then this is the circuit board for communication. And the payload here, this is the different payload in our case. Sorry, in our case we have radiation sensor, or you can have the camera. So based on your mission, what you wanted to take a picture, measurement of the radiation, based on that you have different sensors, and for that we call it payload. And you can select payload based on your requirements. And you have the ground station. So we have the signal sent down from the satellite we receive with the help of this thing. And now this is a ground station for simpler tests. For our purpose, we have a larger ground station. And this is the training we give in Nepal and outside of Nepal. So maybe in future, after or maybe while you are doing your undergrad studies, maybe you can join to the similar training in future to learn more in details. And this is our homepage. Maybe you can go into orionspace.com.np and to see what we are doing. We have workshops, career. Maybe in future you can come and join about us, our team members. So you can go and visit our homepage. So thank you very much. This is a very brief and short introduction about the space technology and satellite, and then what we are doing in Nepal. And you already saw a picture of our satellite. This is the satellite we are soon sending into space. If you have any questions, please ask now, and I'll be very happy to share. Thank you.
Hello, Rakesh. Hello.
Hazur, namaste.
Hazur, namaskar. Rakesh, एकदमै we are really enticed by your presentation है. अनि जुन चाहिँ तपाईले काम गर्नुभएको छ, जुन चाहिँ प्रेजेन्टेसनको फ्लो छ, we really appreciated that one. अनि हजुरको समय busy schedule लाई पनि you gave it for high school students, so we are really inspired by that as well. Sansi, are you there?
Yes, sir.
Yeah, please continue. Okay.
Okay, sure, sir. So thank you so much, Rakesh Chandra, sir. Your presentation, I'm pretty sure it gave insight to all of our participants, and we are very, very honored to be learning from you, because I know this is like once in a lifetime opportunity. And I think we should move on to questions, shall we? So, so we have this one question from our participant. If any one of us have any questions, please drop down in the chats below, and I will convey it to Sir. So one of them have asked, is Voyager a microsatellite?
Oh, okay. Voyager is not the. Well, so satellite is something that revolves around the Earth, right? And Voyager, it is not revolving. It left the Earth, so we can't call it satellite, and then we call it spacecraft. And Voyager 1 and 2, it was launched. I can't remember the date. Maybe in 80s. But I mean, you can check when it was launched. But it is a spacecraft that left the Earth and solar system. So for that, I mentioned already that the orbit the speed of the spacecraft should be very high, that you are able to leave the Earth gravitational field. And then again, if you left the Earth, let's say you left the Earth gravitational field, and then you are still bound by the sun gravitational field. Remember, like Earth is going around the sun. So in one illustration, you saw that Earth is going around the sun and the satellite is going around the Earth. So that means everything is bound by the respective gravitational force. Like Earth is bounded by the sun gravitational force, and satellite is bound by the Earth gravitational force. So to skip this bound and to fly away, you need a very high speed. And it is also called like escape velocity. Maybe you can Google a little bit on that. But now I come back to Voyager again. So the Voyager, which was launched, I don't remember the exact date, which already skipped the Earth gravitational field, and then it is under the sun gravitational field, and then it also skipped the sun gravitational field, and now it's going further and further away. And this Voyager is one of the man-made object which has reached farthest distance now. This is very important to remember, that this is the man-made object which has reached farthest out in the solar system. I mean, it already left the solar system and is still going further.
Okay, thank you so much, sir. I hope, Vishweshwar, your question is answered. So, sir, there is another question from Akriti Paudel, and she asks that how is the communication actually done between the satellites and the Earth? So, doesn't space radiations affect the communication? So, that's what she asked.
Okay, this is very interesting question. So basically, I already mentioned that we have communication. So basically, what is communication? I mean, communication, it could be like you beat the drum here and you hear the sound and you can communicate like, oh, okay, he's giving me a signal to be attention, right? That's how we used to communicate long back. Like somebody on top of the hill will beat the drum, and it will send our attention signal like, oh, get attention or be aware something danger is coming. So beating drum, and that is the sound. So this is how we communicate before the radio signal was discovered, right? Now we have radio signal, electromagnetic. Sound is also the wave, but it's a different wave, and electromagnetic wave is now what we have here is, for example, communication like radio. You can turn on the radio FM and you can get the answer. You can hear them and you can get the communication, like somebody on the radio presenter will tell you something. So this is also communication, right? And now as we go further and further, now we have satellite and Earth. So how can we communicate between the satellite and the Earth? Basically, we are using again this radio communication link, like the one we described, this FM station. So they are the same, but the different in frequency, different band. Like FM is around 90 point something megahertz. Like you can hear them repetitively telling you what is the frequency that you have to tune. So for satellite, we have also the same thing, but then at a different band. So to listen to the satellite, you have to tune to this given frequency. And for example, like there are many different band and different frequency, but for the particular example, in our case, the satellite we built, we are using 400, just to give you a rough number, like 430 megahertz. I mean, just a rough number, just to give you the sense of the frequency. So this is the frequency that we are sending signal. And this is electromagnetic wave, right? And then we have to modulate and demodulate, just like you do, like FM signal. The radio presenter speaks something, the sound is converted into electromagnetic wave and transmit into the the channel we call, and the in between these, like, we have antenna. So antenna one that transmits and antenna one that receives. And after the receive of the signal, you convert back into the electrical signal and then back to the sound. So similarly, in our case, we have ground station where there is a big antenna, and we have a satellite where it's a smaller antenna, right? And the satellite will send signal via like transmitted via the antenna of the satellite. And we have a ground station where there is a bigger antenna to capture this signal, and then there will be some processing like demodulation electronics, and that will generate finally the signal. Meaningful signal, meaningful means understandable, like what you will look at it and say, ah, okay, this is the message I received. Until that, we are, if you do not understand what you are receiving, it's still a communication, but not the complete communication. So it could be a picture, then at the final you will see the picture. This is how we do, and the communication is by the electromagnetic.
Okay. Thank you so much, sir. I hope Akriti Paudel, your question is answered. So now we have another really interesting question by Lucky Shaha. He asks, is it possible to send satellites out of the Milky Way galaxy?
Uh-huh. So, I mean, sending anywhere, any place is not a problem. I already mentioned that the bigger is the satellite or spacecraft, the more fuel, the power you need, right? So you don't want to, build too much bigger. But let's say like you have a smaller one. Now you want to send it outside the galaxy. So there is already a project. They want to go to Proxima Centauri, so another galaxy, which we can do it. But then again, I will come back to the point that you have to leave the Earth gravitational field first, and for that you need a certain speed or the energy. And then after you leave the Earth, you have a solar gravitational field, the sun, and you have to also leave that. Again, like you go further out, like to leave the sun gravitational field is also very difficult. And then the more you are going skipping Earth and skipping sun, is that means you are gaining more and more speed. Otherwise you cannot escape these Earth or the sun. So you have to get more speed. So how can we gain more speed? So one way to do that, you have smaller rockets in your satellite or spacecraft. So the rocket will fire, and then you get some push, and each push will add speed. So you need more of these burning. So and then, like, if you have one burn, the fuel, and that will push your satellite or a spacecraft ahead. And now you have gain small velocity, let's say like from 10 kilometer per second to 11 kilometer per second. And now you have to understand what is the skip velocity of the Earth gravitational field. So you have to get higher than that. And then you have again the skip velocity for the sun. And then you have to gain more than that velocity. So every burn will add velocity. Uh, 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 that is, the satellite is or spacecraft is moving. So every burn you need to accumulate, because you need to accumulate more speed. So this is the point now. How can you accumulate this, or how can you get this speed gain? So if you put fuel inside and you want to do that, maybe it might not be feasible, because to gain the speed, skip the Earth and sun gravitational field, you might need a lot of fuel, maybe, and there we come up with an idea, like we, in the sense, the scientists, they said, okay, we have this the how to say that, the solar sailing, like the sailing like you have in on the boat. So similarly, you have this open thin foil that opens up, and then it hits by the solar radiation and it get pushed. So this is one way to, not to carry lots of fuel, but then use available force in the space that you can push your satellite and drive away. So this is one way to do that. Otherwise, if you imagine like, okay, I will put all the necessary fuel and sand, maybe that will not be feasible. Theoretically speaking, you can do the engineering, maybe it is not feasible. That the point you have to understand is you need to able to gain the speed that can leave the Earth and Sun and other field like as you said Milky Way galaxy, like they have also this accumulative attraction, right? You have to skip this attraction, so you need more speed to break the bond. So this is the point you have to understand. The how are you going to gain this speed? If you are able to do that, you are able to leave the Milky Way and go into another galaxy. Yeah.
Thank you so much, sir. Now, I hope, Lucky Shaha, your question was answered. So we have another student, Anmol, asking you another question. That is, what are your views on extraterrestrial beings, or
Okay.
aka aliens?
Okay. Basically, I mean, this is out of our topic, but still, I will try to explain. So basically, as we human are curious and we want to explore and understand, are we alone in the universe, right? This is what we are searching for the long time. SETI, they are doing this for a long time. So what we do is we are listening to the signal, hoping that they will also transmit, you know, the signal that we are listening, and then we can verify that they exist. And but then there are also probability equation, like what is the probability of finding another civilization. So I forgot the name of the equation. Like you can do this and find out like what is the probability of finding another civilization. So I mean, we have not hear anything from from them or the extraterrestrial, but the search is going on. But yeah, we don't know.
Okay. Mhm.
Maybe there could be. It's a universe is very huge and
Vast. Yeah.
fast.
Okay, so thank you so much, sir. So I'm gonna merge two questions by Mahesh Thakuri and Pramila Sunar. So one, Mahesh Thakuri asks that how is nanosat, I guess, how is nanosat different than the satellite launched by the government? And the other question is that can we see nanosat one from Earth's surface at night?
Mhm. Okay, so how is it different? So basically, there are different parameters to compare. One comparison would be the size. So the government, NAS, they built this in Japan, and the size is 10 centimeter cube. And the one we are building in Nepal, it's 5 centimeter cube. But still the basic building blocks, they are same, like same in the sense they also have the communication system, we also have the communication system, they have also the power supply, we have also the power supply, they have also the processor, we have also the processor or the microcontroller. So functionally they are same, right? Like one human is same to the another human, let's say like that, functionally. But then how one human is different from another, it could be the size, like one is tall, one is short. So it depends how you want to compare them. So the one that built by NAST, it was funded by NAST and built in Japan, and it was a student project. So two of the Nepali students went to Japan to study, and then they did this project to build the satellite in Japan. And whereas in our case, we have our students and engineers working in Nepal and building this satellite in Nepal. So, I mean, they are quite similar in this term. And maybe other topic could be the how expensive they are. Like, I can't remember. It was already in the news, like how much they paid for this, how much the NAST funded to build this satellite, you know. And for our satellite, we already had how much, roughly like 20K, like already, and in Nepali, it would be like 30 lakh. Nepali rupees, so we already spent, and we are all searching for more money to launch, because I already mentioned that to launch satellite is another, buy the ticket, the rocket ticket, and that is very expensive. The more bigger the satellite, the more you have to pay. So we decide to build smaller one. That means we have less money to pay. And how much? Well, I have a here. This is the typical size of our satellite. So this we are launching, and this is just the model. This is not the satellite. Okay, and just to give you the hints, the size. So this is the size of the satellite, and for to launch this, we need to pay 25,000 euro, which is about 30 lakh Nepali rupees. So you can imagine, like, why size matter, because we don't have too much money, and so we decide to be smaller. But then this one is quite similar to the government launched last year, or maybe already 1.5 year ago. And what else? Yeah. And the second question I forgot. Was it?
Second question was, can we see nanosat one at night on the Earth's
Okay,
surface?
okay, 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 okay. I doubt we could see that. I mean, with the naked eye, we can see a, a small light, kind of a small passing, like, which is already International Space Station. You can, in a good clear night sky, you can see International Space Station. But I doubt if we could see a small satellite like these. But then there is a project in Japan, like maybe in Italy, or I think it was in Italy. They are putting light on the satellite, LED LED, and they want to see the satellite from the ground. This is, there is a project going on, but I have no idea, like, if we could see such a small satellite from the ground.
Okay, sir. Thank you so much. I hope your questions were answered. So I will be skipping some questions as we do not have a lot of time. So I will move like towards Apil's question. So he asks that can we absorb hydrogen from space and freeze it to minus 258.87 degree in rocket to make liquid hydrogen or going further in space?
Uh-huh. This is interesting, but so we talked about the satellite that revolves around the Earth. We talked about the Voyager, which left the Earth and solar system. And for everything, we already know that we need a power supply, right? Without the power supply, you cannot do anything. Like in Nepal, like when we don't have electricity, you have to sit quiet and do, like, same in satellite. If you don't have power, you cannot do what you would like to do. And for that, we need to find source of power. And as I mentioned, in our satellite, we have power, solar cell. So that means we are getting power from the sunlight and convert into electric energy and, say, store in battery and use it later on, right? But what if the satellite is not going around the Earth but leaving the solar system? That means the power supply, the solar cell we put on the surface of the satellite will be no use, because it's going further and further away from sun. That means you are not getting any sunlight or energy. So you have to be able to differentiate what is your mission. Is it going around the Earth? Is it going leaving the solar system? And that you have to define. Based on that, how are you going to supply the power? So if you are leaving the Earth and solar system, you are not going to use solar cell. That's for sure. And in that scenario, we are using what we call uh, how is it called, radio isotope, or it's just the nuclear based power supply generator. So this is one option. And now coming to the point about the hydrogen, I'm not sure. I mean, I never heard about this, but getting hydrogen from the space where the spacecraft is and converting into maybe liquid hydrogen, or I don't know in details how they work. But then for that also you need energy to get the hydrogen and use and convert into usable hydrogen. So somehow maybe it might not be feasible. Theoretically, maybe it might work, what you are saying, but then is it feasible? This is another topic we need to discuss, right? So for such application, like if you're going like Voyager, they also have these power supply for used.
Okay.
So I don't know, like if you are able to use hydrogen, but you can also find how other projects, what other people used, how they did it, just to get an idea. Yeah.
Okay. So thank you so much, sir, and thank you so much, Abdul, for your question. So as we're running out of time, I'd like to ask another question by Pravesh Shrestha. So he asks that was at Mega 328 the best microcontroller for Sanosat 1 because it only has 32
Hmm.
KB of memory.
Yeah, this is very interesting. I mean, going deeper into technology.
Mhm.
So basically, our satellite is very small, and what we are using is receiving short messages and transmitting this short message, and the radiation sensor is measuring and then transmitting the measurement. So for our application, this is good enough. But when we do all the coding, I mean, there are other parts that you need to look for, like during the code, like when to take the measurement, and then the antenna deployment and everything. So the code will become longer and longer. But we are at the very verge, like this is just right enough for our application. And in future, if you are doing more complex application, maybe we will have to change to other microcontroller. But then we have um, you can also ask, like, why did we choose this one? Because
Yeah.
I told you, like, we made the model of satellite, right? Before we built this one. And during the model, we use this at mega microcontroller. So we said we will stick with this because all the learnings are in our at mega chip. But then there are other microcontroller too. But then we will have to relearn and study and do all these, which is time consuming again. So we said this one we already know how to build, this one we already know how to use it. So, and this is good enough for our application, so we stick on that. The other topic is very important topic is what is the power consumption of this microcontroller. This is very important because in space we are limited by two things. One, the size. You cannot put everything that you want in this very small size, and the power that you generate is very small. So the microcontroller that is power hungry is not good for the application. That's for obvious, right? If the microcontroller is draining the battery and you are not able to do other applications, so you have to be careful. Like one is that you should be able to fit everything within this size, and also you should be able to operate everything within the power that you generate with solar cell of this size, so which is roughly 20 250 milliwatt. So this is roughly about the USB cable that the USB memory stick. That is a similar power that you generate. It's not, you can't do very huge tasks. That's why we have to be careful whilst choosing the controller, that it is not power hungry and it's not very complex also. So for our application, this is good enough. So we stick with this. Yeah.
Okay. So thank you so much, sir. We have exceeded our time, but I see another interesting question, sir. Will you be accepting one more question?
Sure, sure. I'm very happy. I have
Okay.
time, and I will be happy to answer. all students.
Okay, thank you so much, sir. So we have this question from Prasiddha, and he asks, "What are your thoughts on Elon Musk's plan to build a self-sustaining city on the red planet by 2050?
Mhm.
Will it be possible?"
Okay, this is very interesting. Um, well, I mean, we can't say impossible, right? Because we don't know. I mean, I already showed you how this human civilization moved from geocentric idea that sun is going around the earth. That's how we started, and now we have this. It's not the sun that goes around. Now Earth is going around the sun, and then from Newton to Einstein and further on. So I mean, we can't say impossible. Maybe we are developing every year a little bit. So it's just a matter of time, I guess. I'm now based on the rocket he's building, you know, the reusable rocket and more efficient rocket. So I would say it is much of question of the time rather than is it possible or impossible.
Okay.
And the other topic would be like, can we survive in like to live in the I mean on the earth is very easy because of this, all life supporting like atmosphere with the proper ratio of oxygen, nitrogen, and everything, the water. So we have to be careful, like what are the support system of human. So are we able to fulfill this basic requirement
Mhm.
after we go to Mars? I mean, going to Mars, maybe I wouldn't say it will be possible because we already have sending spacecraft to Mars. So technically, we can send something to Mars, right? It's just a matter of human. Can we send human? But then we are not doing that because until and unless we are certain that the person will not die, we will not kill, we are not sending. This is more ethical part rather than science or technology. Otherwise, as we were able to send bigger rover, Mars rover, similarly, we can put human in instead of Mars rover and land the human on the Mars. This is possible. Technically, it's not a big deal.
Mhm.
But now the
Yeah.
point is, when we send the human, is he going to survive? Are we sure that he will survive, right? This is important. And after he land on the Mars without any crash, and for the living, like, can he sustain the life? This is another topic that you need to answer, like where he will get the water, food, and social life. Because if you are living alone, maybe you get a different kind of problem, like health problem or psychological problem. So it's not just about sending man and possible and impossible. It's just a matter of time, like when we will send the human, and
Uh-huh.
how we will build a sustainable, life-sustaining
Right.
technology for him. This is
Exactly. So, sir, this is the last question, and she asks, "What type of fuel is used in rockets?"
uh-huh. Okay. So I mean, basically, there are different rockets that you need to understand. And I also forgot. I mean, I studied a long time ago. I'm not into rockets, so I can't remember right away
So,
because I'm
someone
more
says
focused
that's
into
liquid
satellite.
oxygen.
Yeah, I mean, yes, that this is one part, but then I was going to say that, um, of course, liquid oxygen and this, what was that, hydrogen, liquid hydrogen, I think they are mixing, and this is a whole different technology. But then again, the point
Mhm.
was that the rocket that you use on the surface of the Earth and the
Uh-huh.
space, they are again different, you know. And again, there is how do we select the rocket fuel or the rocket energy engine or motor? This is again a big, this is a whole different field of study. Like we call it ISP. How do we measure life petrol or diesel, or there are different things that you can use.
Mhm.
Similarly, in rocket, there are also different fuel mechanism and technology, but then you have to choose for your application, like which is the best. And right now, I don't remember. Sorry for that. But one thing I would remind that it is finally breaking down into the parameter called ASP,
Mhm.
impulse
Mhm.
specific anyway, so it's a parameter like quite similar to mileage, right? How much mileage you get. So by burning how much fuel, you get how much delta V. So I already mentioned that the rocket of the spacecraft that goes up, and to leave the
Mhm.
Earth surface, you need this increase in velocity, right? And that velocity is known as delta V, velocity as V. Delta is the change in velocity. So every time you are increase for any application, you need delta V, right? So anyway, now you will compare which fuel will suits you to acquire this necessary delta V. And
Mhm.
just to compare two things, like there are like solid fuel, liquid fuel, and electrical. I mean, there are many technologies, so I'm not able to go into it right now. But then, just to give you the feeling, uh, solid fuel rockets, they are very strong. They are very good for the
Mhm.
higher impulse. So you want to lift the
Mhm.
rocket, leave the earth, and rise up. There you need a very strong engine, and there you need solid rocket. And but then once a
Mhm.
solid rocket is burned, you cannot stop it, and then it's not so convenient. Then we talk about liquid hydrogen and oxygen, I guess. um, there you have the possibility to turn on and off the engine. So there, this is the advantage. And this is also the ISP of this is quite close to solid rocket, but less than solid rocket. So it is still used to lift the rocket up. Once you are in the space, you will use something. One of the best would be like electrical propulsion, right? So
Mhm.
rocket is like it's just a propulsion system, and there is electrical propulsion which is used in space. But how you do is like you are ionizing and then shooting these ions out, just like the fuel burning, shooting the fuel, or the how to say. So basically, in electrical propulsion, that you have these ions that you generate with the higher, and then you shoot with this higher potential difference, because you have this positive and negative plate, and then ions out. And as this goes away, and based on the conservation of momentum,
Mhm.
the rocket or the spacecraft should move forward. So this is the basic idea. Finally, it's the conservation of momentum that we have to look. And then it is again, it is the ISP parameter that you have to look. And then you have to be able to select which technology to use for what application. So this is the overview, but right now, I don't know like how detailed and what exactly.
Mhm. Okay. Okay, thank you so much, sir. Today we had an amazing session. Thank you so much for giving your precious time to us. In such a short notice, you came and gave such an amazing session. Everyone is very happy. We can see it on the chats. Everyone is very thankful. You answered to their questions in depth, and I'm pretty sure that the students are very satisfied and happy as well, and more curious and into science, hopefully. So, thank you so much, sir, for giving your precious time to us and spending extra time for answering our questions. We are very grateful, as well as COPSNs grateful, the students are grateful, and thank you so much, sir.
Thank you very much, and I'm very happy that we have these curious students and very strong questions. And brief overview, but then during question answer, we try to look into a little deeper.
Mm.
But I
Yeah.
think the world is open. You can learn more. If you have any questions, you can contact me via email. I think there was on the site. So I'm very happy to interact with the students. Thank you very much.
Thank you so much, sir. Thank you so much, sir. I think
Okay,
it's
bye.
time to end our session now. Thank you so much for sticking with us for all these 3 hours. And thank you so much, everyone. Thank you, sir. Thank you, all the participants, for being here. We are very grateful, honored to have your presence here. See you tomorrow because we will be having better and amazing sessions tomorrow as well. So thank you so much, everyone. Please, you have to take a leave. And yes, sir, I think we should be all leaving, I guess.
Okay, thank you. Bye-bye.
Thank you, sir.
Have a good time. Thank you. Bye bye, sir.
Okay,
Thank you.
welcome. Bye-bye. Okay.